1943, northern France. A German locomotive stands taking on coal at a rural siding, crews working quickly in the winter cold. Nothing about the heap beside the track suggests danger. A stoker lifts a single lump and throws it into the firebox. And all of a sudden, time stands still. The explosion is instant, a sharp flash, a rupture of steam, and a locomotive left stalled and broken within seconds. To investigators, it will appear as another boiler accident, one of many that winter. But not all of those failures were accidents. In this video, we'll explore the chilling truth about this disaster, a truth that benefited one country, a country who would later defeat the Nazis, and more importantly, win the war. The explosion on that rural siding was shocking, but the circumstances surrounding it were not unusual. By 1943, Germany's railways were carrying the full strain of a continental war. Every front, every garrison, every factory depended on coal-fired locomotives running without interruption. The system worked only because trains moved constantly, thousands of engines feeding on coal drawn from occupied mines and transported to depots across Europe. This dependency created a vulnerability that was well understood in London. Traditional sabotage could damage track, but rails could be replaced within hours. Bridges were valuable targets, yet heavily guarded and costly to attack. Destroying a locomotive, however, carried a far greater effect. Each one represented months of industrial effort, specialist manufacturing, and trained crews who were not easily replaced. If locomotives could be disabled in significant numbers, even briefly, entire sectors of the German logistical network would slow or stall. But sabotage teams faced a fundamental obstacle. Getting close enough to a locomotive to place charges was dangerous, often impossible. Coal yards, sidings, and locomotive sheds were patrolled. Resistance groups varied in skill and equipment, and many lacked the training required for complex demolition work. Any device that required careful placement or precise timing risked failure or exposure. The problem Britain confronted was therefore simple to state but difficult to solve. How could a locomotive be destroyed without approaching it, without handling it at the moment of attack, and without leaving evidence of sabotage? The answer required a weapon that did not look like a weapon at all. Something that could be dropped into a coal pile by anyone, a railway labourer, a passing agent, or a resistance member with only seconds to act. Something indistinguishable from the fuel German crews handled every day. That concept introduced new difficulties. A device hidden in coal would need to survive rough handling, long storage, cold weather, and transport. It had to blend perfectly with whatever local coal type was used. And above all, it needed to detonate only when exposed to the intense heat inside a locomotive firebox. Addressing these challenges would lead British engineers into a specialized field of disguise, materials research, and explosive design unlike anything attempted before. Work that soon fell to the clandestine workshops of the Special Operations Executive. Their efforts and the unusual methods they adopted form the next part of this story. As British planners examined the vulnerability of German rail transport, one conclusion kept resurfacing. Conventional explosives were insufficient. The problem was not destructive power, but access. Locomotives rarely sat unguarded, and resistance networks could not rely on favorable conditions or specialized training. What Britain required was a device that could move through enemy territory, disguised as something so commonplace that no guard would ever think to examine it. Coal, available everywhere and handled constantly, offered precisely that opportunity. Yet turning the idea into a practical weapon demanded a level of craftsmanship far beyond ordinary ordnance work. The responsibility fell to the Special Operations Executive and its dispersed network of research stations. These were not military factories in the traditional sense, but small, adaptable workshops working under strict secrecy. Their remit was to produce equipment for irregular warfare, devices that concealed their purpose, survived harsh environments, and could be used by untrained operatives in the field. Early experiments explored the simplest approach, drilling cavities into real coal and packing them with explosive, but the method proved unreliable. Coal fractured easily, and concealment was inconsistent. A disguised device that crumbled in a handler's hands would never survive the rough treatment of a coal yard, let alone transport across occupied territory. This difficulty led engineers to reconsider coal not merely as a material, but as an appearance to be replicated. If natural coal could not be modified reliably, an artificial shell might provide the durability and camouflage required. At several SOE facilities, including those responsible for camouflage and deception work, technicians drew upon their experience in molding props, replicating textures, and matching colors under varied lighting. The task was painstaking. Coal differed in color, sheen, and fracture pattern across Europe. A lump suitable for northern France looked different from one drawn from Polish mines or the Ruhr. The device therefore needed variants, each tailored to local supplies. Meanwhile, explosive specialists faced their own constraints. The charge had to be powerful enough to rupture a boiler when contained within a firebox, yet safe to transport and handle. Plastic explosives offered the necessary stability, but ignition demanded careful engineering. A detonator triggered by impact or vibration was too risky. The device needed a mechanism that responded only to the sustained heat inside a furnace. Heat-sensitive fuses and insulated housings were tested, refined, and tested again, each prototype submitted to controlled trials to ensure reliability without premature activation. As prototypes improved, attention turned to production. Devices had to be manufactured in sufficient numbers to justify their distribution by air. Workshops capable of small-scale craftwork were adapted to produce consistent molds, and storage facilities were designated for packaging and shipment. Throughout, secrecy remained paramount. Instructions were compartmentalized, and only those responsible for specific components knew the full purpose of the device. These efforts eventually converged, materials research, explosive engineering, and camouflage expertise aligning to produce a disguised weapon robust enough for clandestine distribution. Resistance groups required only a moment near a coal pile to deploy one, and often did so without knowing the full complexity behind its manufacture. Yet even with a viable design in hand, a larger question remained unanswered. What, precisely, had Britain created, and how would this unusual device function when placed inside an enemy firebox? That answer forms the reveal that follows. The result of SOE's fragmented, highly specialized development effort was a device outwardly indistinguishable from the coal it sought to replace. To the eye, it appeared as nothing more than a rough, irregular lump of fuel, matte or glossy, dark or brownish depending on the regional variant. What set it apart lay entirely within its casing. At its core sat a small charge of stable plastic explosive, paired with a heat-responsive firing element enclosed within a shell shaped and finished to match local coal stocks. Its purpose was straightforward. Once mixed among genuine fuel, the device required no further handling. When a locomotive fireman unknowingly fed it into the firebox, the intense heat would activate the internal element and drive the charge to detonation inside the confined space of the furnace. The explosion alone was damaging. The rapid release of pressure inside the boiler was often more so. To German investigators, the result resembled a spontaneous mechanical failure, precisely the ambiguity the designers intended. Yet achieving such simplicity in appearance demanded solutions far more involved than the finished weapon suggested. With the basic concept now clear, the question becomes, how exactly was this disguised explosive constructed? And what allowed it to operate reliably in such harsh conditions? These details emerge in the engineering deep dive that follows. The simplicity of the disguised coal lump belied the technical complexity concealed within it. Having created a workable concept, SOE's engineers now faced the challenge of turning it into a device that could survive the physical realities of wartime handling. Coal storage sites were not gentle environments. Lumps were shoveled, dropped, crushed under weight, and exposed to cold, damp conditions. A weapon disguised as fuel had to endure all of this without deforming or losing its disguise. To achieve this, the design adopted a layered construction approach. At its heart sat a compact charge of plastic explosive. Records refer to stable formulations that could tolerate rough treatment while retaining predictable performance. The charge was shaped to fit within a relatively small cavity, so that the outward appearance of the device remained consistent with local coal. Surrounding it was a shell formed either from molded material or, in earlier forms, from reinforced fragments of real coal. The molded types proved most effective. Artificial shells could be produced in identical halves, each dyed and textured to match specific regional fuels. Once filled, the halves were sealed together and coated with real coal dust, giving the surface a convincing irregularity. Ignition presented a separate set of engineering requirements. The device had to remain inert throughout handling, yet respond reliably to the heat of a firebox. SOE adopted a heat-sensitive triggering component, enclosed with the main charge to insulate it from ambient conditions. Only when exposed to the sustained high temperatures inside a furnace would the element activate the detonator. This avoided the hazards of impact or vibration-sensitive systems, which would have been unsuitable given the rough conditions of transport and storage. In operation, the sequence was straightforward. Once inside the firebox, the shell began to heat rapidly. As its temperature rose, the internal fuse or chemical element reached its activation point, initiating the detonator, which in turn drove the main charge. The blast, though modest in quantity, occurred within a confined space lined by steel plates already under pressure. Boiler construction relies on balanced stresses. A sudden localized shock could fracture plates, displace rivets, or rupture tubes. Whether every detonation would fully destroy a locomotive remains uncertain. Documentation does not provide results of controlled trials, but the engineering logic behind such damage is sound. A boiler operating under load was particularly vulnerable to the rapid pressure release that followed a breach. The shells themselves underwent continual refinement. Early drilled coal versions proved brittle and inconsistent, their surfaces prone to revealing tampering. Later, molded forms allowed engineers to vary size, shape, and surface characteristics with considerable accuracy. This addressed a key problem. Coal drawn from different regions behaved differently under light. Anthracite, for example, presented a hard, glossy surface, while lignite appeared dull and brown. Producing region-specific variants helped ensure that resistance groups could deploy devices indistinguishable from local stocks, reducing the risk of detection by experienced coal handlers. Durability also shaped internal construction. Metal housings were introduced to contain the explosive and protect the firing element, surrounded by plaster or filler to maintain the outward coal form. This design protected the internal components from crushing forces and provided a consistent exterior surface. Moisture resistance was another factor. Coatings and sealants were applied to prevent damp conditions from degrading the fuse or contaminating the explosive. Distribution imposed its own constraints. Devices were packed carefully to avoid friction damage, then shipped or airdropped to resistance networks. Once in the field, local operatives typically inserted them discreetly into coal piles or directly into locomotive tenders. This simplicity of deployment was central to the concept. The engineering complexity existed entirely on the British side, allowing field use by individuals with no specialist knowledge. Despite their sophistication, these devices were not infallible. Poor placement, damp conditions, or insufficient furnace temperatures could reduce their effectiveness. Some may never have detonated at all, but each successful use carried an impact far greater than the size of the charge suggested. It introduced uncertainty into every coal-fired engine under German control. Yet understanding the full significance of this technology requires returning to the atmosphere of the cold open, to the kind of moment where one anonymous lump of fuel altered the course of an ordinary workday. And it is there, in those quiet places where routine met sabotage, that the next part of the story takes shape. The ruined locomotive in northern France might have seemed an isolated accident, yet scenes much like it unfolded across occupied Europe. Railway crews approached their work with new caution, though few understood the source of their unease. A stoker, facing an evening shift beside a silent engine, would glance at a coal pile with a hesitation that had not existed months earlier. Each shovel load, once taken for granted, now carried a faint but persistent doubt. With the mechanics of the device understood, its effect on the human environment becomes clearer. Steam locomotives demanded close contact with heat, pressure, and machinery already capable of sudden failure. Introducing a disguised explosive into this delicate system transformed routine into latent threat. Even a single detonation, whether or not confirmed as sabotage, could alter behavior along an entire line. Fires were stoked more slowly, heaps inspected more carefully, and crews worked with a tension that did not appear in official records but filtered quietly through occupied territories. And yet, the historical record remains largely silent on measurable outcomes. Railway incidents were logged, repairs undertaken, and replacements ordered, but the true impact of disguised explosives is difficult to quantify. Their success lay not merely in physical damage, but in the uncertainty they introduced, a quality far harder to document. To understand the full consequence of the weapon, we must now merge engineering logic, operational history, and the broader wartime context in which these devices were deployed. Determining the true impact of disguised explosive coal requires examining both the material results and the quieter consequences that seldom entered official records. Production figures survive. Several tons of devices manufactured by SOE and dispatched across occupied Europe, usually by RAF Special Duties squadrons. Their purpose was simple: to introduce a hidden instability into a railway system already strained by distance, weather, and wartime demand. Precise outcomes are harder to trace. Sabotage of this kind was designed to appear accidental. When a locomotive failed under load, investigators frequently attributed it to fatigue or impurities in the fuel. Surviving technical notes from development suggest that detonations within a firebox could displace tubes, split seams, or distort boiler plates sufficiently to disable an engine. Even where the blast did not cause catastrophic failure, it could compel lengthy repairs, require specialist labor, and withdraw a locomotive from service at a moment when replacements were scarce. More significant, perhaps, was the uncertainty the devices created. Railway crews across occupied territories had long worked with machinery whose dangers were familiar and predictable. To introduce the possibility that a routine act, placing fuel into a firebox, might be the trigger for sudden destruction, was to alter the psychological landscape of the railway. Coal heaps, previously ignored, became sources of unease. Work slowed, precautions multiplied. Guards were reassigned simply to watch piles of fuel. The disruption spread well beyond the sites where any explosion occurred. In the broader context of resistance activity, concealed explosives formed only one element among many: track cutting, bridge attacks, derailments, and sabotage of signaling equipment all contributed to the cumulative strain on German logistics. By 1944, rail networks in several regions were operating at reduced capacity, burdened by shortages of equipment and overworked repair crews. Devices hidden within coal cannot be isolated as the decisive factor, but they played their part by targeting the most valuable component of the rail system, the locomotive itself. The idea outlived the war. Intelligence agencies studying industrial sabotage during the early Cold War noted the value of disguised charges that undermined the reliability of critical machinery. Variants appeared in wood, industrial fittings, and even munitions intended for capture. Though technology shifted, the principle remained consistent with the wartime coal device. The most effective sabotage is that which forces an adversary to distrust what they rely upon daily. Yet the full meaning of this invention becomes clearest when returned to the sort of moment with which our story began. A quiet siding in winter, a locomotive under steam, a stoker lifting fuel in the fading light. The coal heap looks ordinary, the routine is unchanged, but the atmosphere is different now, not because of what the men know, but because of what cannot be known from sight or touch alone. Somewhere within the pile may lie a fragment of Allied ingenuity, indistinguishable from the rest, waiting only for heat to reveal itself. In that pause before the next shovel load, the entire purpose of the weapon is expressed. It did not rely on spectacle or certainty. Its power lay in the hesitation it created, the doubt it seeded, and the quiet disruption it introduced into an occupied railway system. And when the firebox door opens once more, casting its familiar glow across the yard, the memory of past explosions lingers, a reminder that even the most ordinary fuel could carry the weight of sabotage. Here, the story finds its conclusion, in the understated but enduring influence of a device that blurred the boundary between routine and threat, engineering and illusion, coal and concealed explosive.